Hello, good morning students. In the previous class we started with the Thyristor, okay, and we discussed about the introduction of Thyristor, the constructional feature of Thyristor, and also we discussed about the characteristics, VI characteristics of Thyristors, and we discussed a few of the terminologies related to the VI characteristics like latching current, holding current, then breakdown voltage, okay, and how the comparison of latching and holding current and other part we discussed in the previous session. In this session we'll discuss about the another important topic related to the thyristor, that is a two transistor analogy or two transistor model of thyristors. Okay, so this the regenerative or the latching action. So latching action is due to the positive feedback which can be demonstrated by using your two transistor analogy. The latching action can be demonstrated by using this two transistor analogy here. Thyristor can be considered as a two complementary transistor here. In this case, the thyristor is considered as a, these are some of the few of the expected questions and the previous year question papers they are asked in the various question banks. Okay, these are few of the questions listed, so you may get any questions like this. So many times it is asked, it's you can just take it as an important concept. Okay, so many times this is asked. So this is a schematic representation of a two transistor analogy of a thyristor. You can just see here two transistors are connected. This is your NPN transistor. This is your actual PNPN for 4-layer 3-junction transistor, anode, cathode and gate. Okay, so it is splitted into two transistors. So two transistors, so one PNP transistor and one NPN transistor. As it's a PN structure, it is PNP NPN. So two transistors are combined to form a thyristor here. So this is the cross-sectional view of the two transistor analogy of a thyristor, and whereas this is the sectional equivalent circuit of two transistor analogy of a thyristor. So here it's a IA is the anode current, so IC2 is the collector current of the thyristor 2, AE1 is the collector 2, so IB2 is the base current of the transistor, IB1 is the base current of the transistor 1. So gate of this one, anode and cathode. So two transistors are connected in an anti-parallel fashion here. So two transistors connected in an anti-parallel fashion. So here the thyristor can be considered as a two complementary transistors. They are connected in an anti-parallel fashion. One is a PNP transistor, that is Q1. You can say Q1 is a PNP. Just a second. PNP transistor and NPN transistors. So Q2 is a NPN transistor which are shown in the figure here. So the equivalent circuit is this is the complete equivalent circuit of a two transistor analogy of a thyristor. Okay, so the collector current IC of a thyristor is related in general to the emitter current IE and the leakage current IC. So in generally the collector current is linked with the emitter current, okay, and the leakage current. So it is given as, so the operation of this is explained here now. The operation of the thyristor can be explained with the help of the two transistor model, two transistors NPN and PNP transistors, which is shown in the figure. So the middle of two layers are split into two separate parts. So the middle layer is nothing but this one. So here PN, the middle of both is nothing but NP. So these are split into two separate parts. Okay, so because of this two transistors are formed. So as the NP structure is split into two parts, so two transistors are formed here. So the transistor Q1 is of PNP and transistor Q2 is of NPN type here. Okay, the base of Q1 is connected to the collector of Q2. You can just observe in the figure here. So base of Q1 is connected to collector of Q2. So the emitter of this collector of Q1 is connected to base of Q2 here. So this is the connection diagram. So these transistors are in a common base configuration, so common base configuration mode, and general the relationship between this collector current IC and the emitter current IE and the leakage, they are interrelated. The collector current, emitter current and the leakage current all are the interrelated. So the collector current is of this particular transistor IC is equal to, so collector current relation is IC is equal to alpha into IE plus ICBO. ICBO is nothing but the leakage current. ICBO is the leakage current, where alpha is nothing but the gain. So it's a ratio of IC, collector current divided by emitter current. So common base gain, it is called as a gain of an transistor. So it's a ratio of a collector current divided by emitter current. So this is a generalized equation for the collector current of a transistor. So now we will write the collector current equation for both the transistor 1 and transistor 2. So IC1 is equal to alpha 1 into, so IC1 is equal to alpha in IE1 plus ICBO1, call it as equation number 2, that is a 1. So similarly from the figure, so IE1 is equal to IA, you can just go to figure now. So IE1 is equal to IA, just a minute. So here, see here, you can just see here. So IE1 is equal to IA, that means whatever the emitter anode current which is flowing, it's same as the IE1, emitter current of the transistor 1. Okay, see, IE1 is equal to IA, just substitute this IE1 is equal to here in this above equation, you will get IC1 is equal to alpha into IA plus ICBO1, call it as equation number 3. So where alpha 1 is the gain, is current gain of Q1, okay, then ICBO is the leakage current gain of Q1. Q1 is nothing but transistor 1. Similarly, you have to write the collector current equation for transistor 2 also. So now you can see here, so IC2 is equal to alpha 2 IE2, same above equation, the IC2 is equal to alpha 2 IE2 plus ICBO2. ICBO2 is the leakage current, it's a IE2 is the emitter current, and alpha is the gain of the transistor 2. So from the figure C, so IE2 is equal to IK, you can see here. So from the figure C is nothing but this is your figure C. IE2, where is that? IE2, which is equal to IK, that means the collector current of the transistor 2. So IE2 is equal to IK. You substitute that IE2 here and rewrite the equation, you will get IC2 is equal to alpha 2 IK plus ICBO2, call it as equation number 5. So where alpha 2 is the gain, current gain of transistor Q2, and the ICBO2 is the leakage current of the transistor Q2. So from this figure, see, then it is clear that IA is equal to IC1 plus IC2. You can once again go back to the figure here. So IA is equal to, what is that? IA is equal to, so IC2 plus, where is that? IC1. So IC1 and IC2. So IA is equal to IC1 plus IA2. So that is from the figure here. So from the figure it is clear that anode current IA is equal to collector current of transistor 1 and collector current of transistor 2 here. So IA IC1 plus IC2. So is a sum. So substituting equation number 3 and 4. This is the equation number 3 is the IC1 equation, and 4 is the IC2 equation. So substitute equation number 2 and 3 in the equation number 6, you will get. So rewrite it. Okay. So from the figure you know that IK is equal to IA plus IG. So substitute all the equations, simplify, go on simplify it for IA. Okay, so you'll get the IA value as just one step simplification, 2, 3, 4 step simplification you do it, you will be arriving at the equation IA is equal to ICBO1 plus ICBO2 plus alpha 2 IG divided by 1 minus alpha 1 minus alpha 2. So finally the anode current of a transistor, 2 transistor analogy will be IA is equal to ICBO1 plus ICBO2 plus alpha 2 IG divided by 1 minus alpha 1 plus alpha 2. Call it as equation number 2. This is the 7. So it's the equation to calculate the anode current of a thyristor. Okay, so that's so typical variation of the current gain with respect to emitter current. So emitter current IE it is, and it's a gain alpha. So alpha is the gain. So initially what happens, so as the alpha gain is increases, your current is also increases. So at some point the current is also going to saturation mode. So the current gain alpha varies with the emitter current IA is equal to IE. So a typical variation of current gain with emitter is shown in the figure above. Okay, how it is varying. So if the gate current IG is suddenly increased, okay, this immediately increases the anode current. If the gate current increases suddenly, so anode current is also increases suddenly, which would be further increases by alpha 2 and alpha 1. So if gate is increased suddenly, the anode is also increases. So if alpha 1 plus alpha 2 tends to unity, so then the denominator of the equation 3 approaches to 0, so resulting in the large value of the anode current. So if the denominator is approaching to 0, then large anode current will be flowing. The thyristor turns on with a small gate current. In this case, the thyristor will turns on with a very small amount of the gate current. Okay, this is about the two transistor analogy. So you may get the question, as I said in the beginning, so you may get the questions like, so explain using the two transistor model the switching operation of the thyristors and the significance of this during the gate control, and also derive the expressions for the anode current. So you have to explain the each bit of this one. So you have to draw the circuit diagram, and every bit you have to explain, and also you have to deduce the expression for this. So IC1, so you have to generalize the collector current equation you have to write. So then you have to go for IC1, so specifically to the collector transistor 1, and for the transistor 2 same way, just applying just IC1 and IC2. So add those two and calculate the current, anode current of a transistor. Okay, so that's about the two transistor analogy of a thyristor. Okay, so next is next concept is the methods of SCR turn on. So you may once again, it's also asked in the so many times in the previous year question papers. Here are the some of the list of questions which are asked in the different exams. Okay, so this is the questions which are asked in different exams. So for that, there are different methods are there to turn on the SCR with a positive with respect to cathode. The thyristors can be turned on by one of the following techniques. There are different techniques are there to turn on the SCR. So using the gate, so that is a thermal turn on or a high temperature triggering. There is a first one is the thermal turn on or high temperature triggering, then light triggering, another technique. So or the high voltage triggering, then dV by dt triggering, then gate triggering. These are the 5 methods is used for turning off. These are the very important 5 methods most commonly used to turn on the SCR in the power electronic sector. Okay, let me start with one by one. Thermal turn on or a high temperature turn on. So here first one, what happens, the thermal turn on. So if the temperature of the thyristor is high, okay, there is an increase in the number of electron hole pairs. So if the temperature is increased, there is an electron hole pair is also increases. So with the increase in the leakage current, so this increases the currents of causes the alpha and alpha 2 increases. That means the gain is also increases. So alpha 1 plus alpha 2 may tend to go to unity, I mean infinity. Okay, unity, and the thyristor may be turned on. That means as the gain is increases, your thyristor current is anode current is also increases, and the thyristors tend to turn on. Okay, this type of turn on is called as a thermal runaway, and it's normally avoided. It's called as a thermal run on or high temperature turn on or thermal triggering. So this is one way of turning on of a SCR. So next is a light triggering. So if the light is allowed to strike the gate to cathode, there is a high intensity light radiations are allowed to strike the gate and cathode junctions of the thyristor. Okay, then the electron hole pair which will increases the, and the thyristor is turned on. So electron hole pair increases and which will tend to turn on the this one. Okay, next is high voltage or a forward voltage turn on. So what happens here, if the forward anode current, anode to cathode voltage is greater than the forward breakdown voltage VBO, then what happens, the sufficient amount of leakage current flows to initiate the regenerative turn on. So in that case, sufficient amount of current will flows which will initiate the regenerative turn on. So this type of turn on may be destructive and should be avoided. So it may be there is a chances of failure, that may be chances of burning of your SCR, burnout of your SCR may happen. That is why it's somewhat like a destructive phenomenon, so it is avoided in some of the cases. So next is the dV by dt triggering. So dV by dt triggering, so what happens in this case, voltage variation of voltage with respect to time here, dV by dt, that means vary the voltage with respect to time here. So what happens in this case is, if the rate of rise of anode cathode voltage is high, okay, so just concentrate, if the rate of rise of anode cathode voltage is high, then the charging current of the capacitive junction may be sufficient. So if it is high, If the rate of change of anode current is high, then what happens? The charging current of the capacitive junction, charging current of the capacitive may sufficient enough to turn on your SCR. Okay, so the high values of this charging current may damage the transistor, and the device must be protected against the dV by dt. So because of the high values of this charging current, there is a chances of damage of the equipment, so it should be protected from the dV by dt. That's the one thing. So next is a gate triggering. So what happens if the thyristors is forward biased, the junction in the junction if the thyristors is forward biased, the injection of the gate current by applying the positive gate voltage between the gate and the cathode terminal. So we have a gate terminal and a cathode terminal. So by injecting the positive gate supply between the gate and cathode terminal turns on the SCR. So by applying the positive pulse to the gate and emitter, gate and the cathode terminal, anode, cathode and gate here. So if you apply positive gate pulse between the anode and the cathode terminal, then it will triggers the SCR, then the SCR is turns on. So as the gate current is increased, the forward blocking voltage is also increases and the SCR is going to on stage. Okay, that is why, so out of these two, gate triggering is most commonly used. So few of the your high voltage triggering or thermal triggering, there are some destructive phenomenon which mean there is a chances of the failure of the equipments. So that is why they are not most commonly used. So because the gate triggering is one of the easiest way of turning on of SCR, so gate triggering is widely used in the various applications to turn on the SCR. So these are the different methods of turn on of SCR. So what we discussed here, two transistor analogy of SCR, and we have deduced the expressions for the anode current. Then we discussed about the different methods of thyristors turn on we discussed here. In the next class we'll discuss about the another concept, that is switching characteristics of SCR. The switching characteristics of SCR and other related things we will discuss in the next video. So if you got any doubts here in this particular video, you can feel free to contact me anytime. Okay, thank you.